Hello and welcome to lecture 31 of our Essentials of Semiconductor Device Physics course. In this lecture, we begin our analysis of p-n junctions out of equilibrium. So last time we learned that when a semiconductor is taken out of equilibrium, the Fermi level splits into quasi-Fermi levels. And this time, we're going to begin our analysis of properties of p-n junctions out of equilibrium, and we are interested in the particular case where the p-n junction is taken out of equilibrium by connecting it to a circuit. So there are basically two ways we can connect a p-n junction to a circuit, and I'm showing here one of these two ways, which is the forward bias connection or forward bias configuration. So I'm representing here a battery with the higher voltage on this side and the lower voltage on this side, and as you can see, the battery is connected with the higher voltage on the P side and the lower voltage on the N side. So in forward bias, we have higher voltage on the P side and lower voltage on the N side. Actually, in practice, we cannot connect a battery straight to a p-n junction like that because, as we're going to learn in this lecture, in forward bias configuration, the p-n junction conducts very well. It behaves almost as a short circuit. So if we do that, we are essentially short circuiting the battery. So usually we need to plug a resistor to do this connection, but I'm not showing the resistor here to simplify the drawing, to emphasize that in forward bias we have a higher voltage on the P side than on the N side. And this is the symbol for a p-n junction that is used in circuits. It's an arrow. The tail of the arrow is the P side and the tip is the N side. So this is the circuit drawing for a p-n junction in forward bias. And we should have a resistor here that I am omitting. Now notice that if we connect the p-n junction to a battery, there will be a new electric field in the p-n junction. There will be an external electric field due to the battery. And since we are plugging the positive part of the battery, the high voltage part of the battery on the P side and the low voltage on the N, this electric field will point from P to N. In other words, it will be antiparallel to the internal electric field. So the external electric field in forward bias configuration is antiparallel to the internal electric field. This is an important feature that we need to keep in mind. And the current flows from P to N. So the current flows like this, from P to N. And I'm showing here the direction of current flow from P to N. So we have holes flowing from P to N, and we have electrons flowing from N to P. And recall that a flow of electrons from N to P means a current of electrons from P to N. So the current is in the opposite direction of the flow of electrons because electrons have negative charge. The other configuration we can have is the reverse bias. In reverse bias, we connect the higher voltage on the N side and the lower voltage on the P side. And notice now the electric field, the external electric field due to the battery, is now parallel to the internal electric field. So in this case, the total field is higher than the field in equilibrium. So in reverse bias, the total field in the depletion region is higher because the two fields add up. And the direction of current flow is now from N to P. We have holes moving from N to P and electrons moving from P to N. And I am representing here the direction of the current flow, and I drew a thin arrow here as opposed to a thick one here to convey the notion that the current in forward bias is high and the current in reverse bias is low, and we're going to discuss why that is the case in this lecture. And here we have the circuit configuration of a diode, a p-n junction, in reverse bias. So now let's take a closer look at the PN junction in forward bias configuration. But before we do that, let's briefly remind ourselves of the properties of a PN junction in equilibrium, like we discussed in lecture 26. So recall that when the PN junction is in equilibrium, the electrostatic potential difference compensates the chemical potential difference. In other words, there is a drift current caused by the electrostatic potential difference that compensates the diffusion current caused by the chemical potential difference. So what's happening is that electrons are trying to diffuse from N to P, and the electric field is pulling them back. So the current due to the electric field pulling the electrons back is a drift current, which is compensating the diffusion of electrons from N to P. And likewise, holes try to diffuse from P to N, but the electric field pulls them back, and this current due to the electric field pulling the holes back is a drift current, which is compensating or canceling the diffusion of P to N, so that the net flux is zero. The Fermi level is aligned because the electrostatic potential difference is compensating the chemical potential difference between the N and P side, like we discussed in lecture 26. But when we connect the PN junction in forward bias, then there will be an external electric field due to the battery, and this external electric field will be anti-parallel to the internal electric field. So the total field now is lower than the field in equilibrium. So that means that the electrostatic potential difference now is lower than the electrostatic potential difference in equilibrium. Recall that this term here is the work done by the internal electric field. This term here is the same as this. This is still the work done by the field of a PN junction in equilibrium. But now we also have the work done by the external electric field, which is this term here. This stands for external. So this term is the work done by the total field, the internal minus the external electric field. So since this field now is lower than the internal field, we have a lower barrier. So now we can have a net current. We have now a current of holes diffusing from P to N and of electrons diffusing from N to P. And recall that if electrons are moving from N to P, that means that their current is in the direction of P to N, because the current due to electrons is in the opposite direction of the flow of electrons, because electrons have negative charge. Now, recall from lecture 15 and lecture 27 that the diffusion current depends on the gradient of the concentration of charge. And this gradient is very high in a PN junction, because in a PN junction we have a high concentration of electrons on the N side and a very low concentration of electrons in the P side. So the gradient is high. And also we have a high concentration of holes in the P side and a low concentration of holes in the N side. So the gradient is high. So the diffusion current, both of holes and of electrons, is very high in a PN junction in forward bias. In other words, we should expect that the current in forward bias is high. This is a current which is predominantly a diffusion current, and this diffusion current is high because the gradient is high. And that's why we cannot connect a battery straight to a PN junction like that, because this current is so high that the PN junction essentially behaves as a short circuit. So you always need a resistor. And I emphasize that this voltage here, the external voltage, is the voltage across the PN junction, is what we measure if we plug a voltmeter across the PN junction. So for example, if the battery has this voltage here, VB, then this voltage is not VB. It will be the voltage appearing across the PN junction. Now let's take a look at the reverse bias configuration. Now the two fields are parallel, so the total field now is increased. So that means that the electrostatic potential difference now in reverse bias is even higher than in equilibrium. So if this potential difference in equilibrium was already sufficient to prevent the flow of electrons from N to P and of holes from P to N, now that this barrier, this electrostatic potential difference is even higher, then it is even more difficult for electrons to diffuse from N to P and for holes to diffuse from P to N. But in fact, we could have an extra drift current because we have a higher electrostatic potential difference. We have a higher electric field. But this drift current is in this direction. In other words, it's a current that is trying to bring holes from the N to the P side and electrons from the P to the N side. But the concentration of holes in the N side is very low, and the concentration of electrons in the P side is very low. Since this current depends on the concentration of holes in the N side, which is very low, and on the concentration of electrons in the P side, which is also very low, this is a very low current. So the current in reverse bias is very low, and often we can treat the PN junction in reverse bias as if it were an open circuit. Another way to understand the difference between the PN junction in forward and reverse bias is to again resort to the analogy we used in lecture 26 for the PN junction in equilibrium. So recall that the balls here represents electrons, so we have a high concentration of balls on the N side, and then we have a gravitational potential difference which is sufficient to prevent a net flux from N to P. So every ball that goes up ends up coming back due to the drift caused by the gravitational potential difference. So this is the condition in equilibrium. Now the condition in forward bias, we have a lower gravitational potential difference. So now the barrier is lower. Now it's very easy for the balls to diffuse to the other side. And since the concentration in one side is much higher than in the other, this is a high current. So this is the condition of forward bias. Now in reverse bias, we increase the barrier height. So the balls that could not go to the other side in equilibrium, now surely they still cannot go in reverse bias because the barrier is even higher. Any new current would be a current of balls on this side falling to this side. In other words, it's a current that depends on the concentration of electrons in the P side, because we need to take these balls and pull them back. But here I am representing an ideal condition where there are no electrons in the P side, there are no balls on this side here. So this new drift current is zero. So the current in this configuration is zero. Every ball that goes up comes back down. We still have zero current in reverse bias. Actually, we still have a low current because there is some concentration of electrons in the P side, and there is some concentration of holes in the N side. But this current is very low, as we're gonna detail more in the next lectures. Now let's take a closer look at the band diagram of a PN junction out of equilibrium. And to do that, I'm going to assume forward bias. And if you understand the property of the band diagram in forward bias, it's relatively easy to extend the same ideas to reverse bias. So here I'm showing the band diagram in forward bias. We have a lower electrostatic potential difference, as we discussed. But now I want you to notice that instead of having one Fermi level that is constant across the junction, as in the case in equilibrium, now we have two Fermi levels like we discussed in the previous lecture. We have a quasi-Fermi level for electrons, which is represented as the dashed line, and we have a quasi-Fermi level for holes, which is represented as the green line, and none of them are constant across the junction, because the junction is not in equilibrium. If they were constant, we would be in equilibrium. Now we need to understand why they look like that. And to do that, we need to recall the expressions for the concentration of free electrons and the concentration of holes that we derived in lecture 30, the previous lecture, in terms of the quasi-Fermi level for electrons and the quasi-Fermi level for holes. So the important bit to notice here is that the concentration of free electrons depends on the distance between the quasi-Fermi level for electrons and the conduction band, and the concentration of holes depends on the distance between the quasi-Fermi level for holes and the valence band. So let's focus attention now on the concentration of free electrons. So let's focus attention on this equation. Recall that this equation also applies to the energy band in equilibrium as long as we identify this term with the Fermi level. So this is the relevant distance for the concentration of free electrons. So notice that in this region we have a short distance. If we have a short distance, that means that the concentration is high, as you can notice by inspection. If this number here is a small number, then n is a high number, because the exponential has this negative term here. So a short distance means a high concentration of free electrons. Recall that this is the n side. So this short distance here makes sense because we do have a high concentration of free electrons in the n side. Then this concentration reduces across the p-n junction, and when we across the depletion region, and when we reach the p side, then we have a very low concentration of free electrons. That is why the distance now is long. So these long arrows here represent a low concentration of free electrons in the p side. Now let's examine the energy band in forward bias. You can notice that the quasi-Fermi level is constant in the n side, and the distance to the conduction band is basically identical to the distance in equilibrium. So that means that the concentration of free electrons in forward bias condition has not changed with respect to the concentration in equilibrium, since this distance here is basically identical to this distance. And that happens because the concentration is very high. Since the concentration of electrons here is very high, it does not change significantly when we take the junction out of equilibrium. This is why this distance here is basically identical here, and this is why the quasi-Fermi level is constant in the n side. Now when we enter the depletion region, the quasi-Fermi level will change a bit, but this effect is low, so we can ignore it in a first approximation because the p-n junction is usually short in forward bias conditions. So we can ignore this effect, then we are going to consider that the Fermi level is still constant, and then when we enter the p side, like in this edge here, we notice that this distance, because the band is less bent here, so this distance here is considerably shorter than this distance. So that means that the concentration of free electrons on the edge of the depletion region in forward bias is much higher than the concentration in equilibrium. And that makes sense. We have a very low concentration of free electrons on the p side. But now we have an injection of electrons because electrons are diffusing from n to p, and these new electrons arriving here make a very big difference to the concentration because the initial concentration is very low. So we have a significant difference between this arrow and this arrow. We have a much higher concentration of free electrons in the edge here when we are in forward bias than when we are in equilibrium. But we have an excess of electrons. We have more electrons now than we had in equilibrium. So that means that we're going to have recombination. We have more free electrons than in equilibrium, and there are lots of holes for them to recombine. So these electrons will suffer recombination, and they will disappear. The free electrons will cease to be free electrons. So the concentration of free electrons will decrease as we move away from the depletion region. And that is why this distance has to increase as we move away from the depletion region. This is why the Fermi level lowers. I'm representing here a linear decay, but the decay is not actually linear. We're going to consider mathematical analysis in the next two lectures. What is important here is to notice that the Fermi level goes down as we move away from the depletion region, because this distance increases due to the process of recombination. So the concentration lowers due to recombination until it reaches the value of equilibrium. And this point here is the point where this distance is equal to this distance here, which means that the concentration away from the depletion region in forward bias is the same as the concentration in equilibrium, because all new electrons, all extra electrons, recombined before reaching these regions far away from the depletion region. And we can make the same analysis for the quasi-Fermi level for holes. It is constant here, and this distance is the same as in here, because the concentration of holes does not change significantly because it's very high already. But now there will be diffusion of holes to the end side, so this distance here now is much lower than this distance, because the concentration of holes in the end side changed significantly when you took it out of equilibrium, because this concentration was already very low. So any new holes that arrive here makes a big difference to the concentration. So this is why this distance is lower than in here. But then, due to recombination, the concentration of holes decrease, so this distance starts increasing until it reaches the condition of equilibrium, until no new hole reaches a certain distance, all holes recombine. So this is what is represented in this point here. Now let me say a few words about why the quasi-Fermi level on this side is higher than the quasi-Fermi level on this side by this much. So recall that this is the electron's charge and this is the external voltage, the voltage across the p-n junction. So let's suppose we have a p-n junction in forward bias configuration, and we measure the voltage across it and find it to be this number. So let's remind ourselves of what this number means. Now recall that volts are units of joules per coulomb. So that means that if we have a potential difference V external across the p-n junction, then the potential difference is given by this term, the potential units of volts times the charge of an electron. And also recall that in forward bias, the current is flowing in this direction, which means that the electrons themselves are flowing in the opposite direction. So this number means that the potential of the electron gas on this side is higher than the potential on this side by this much. And what is this potential? This must be the total potential, the electrochemical potential, the sum of the chemical and the electrostatic potential. In other words, this must be the Fermi level. So this number means that the Fermi level on this side is higher than the Fermi level on this side by this much. And this is exactly what we are showing here. So we are showing that the Fermi level on this side is higher than the Fermi level on this side by this much. Okay, so now let's take a look at the band diagram in reverse bias. This is the energy band diagram of the junction in reverse bias. So since we are still in a condition out of equilibrium, we have the splitting of the Fermi level into quasi-Fermi levels. So this is the quasi-Fermi level for electrons, quasi-Fermi level for holes. Their difference is still a measure of the external voltage across the junction, just like in forward bias. The potential barrier is higher than in equilibrium, like we already discussed. The quasi-Fermi level is constant for electrons, is constant in the n side because the concentration is high, so it does not change significantly when you take it out of equilibrium. The same applies for holes in this side, and away from the depletion region, the concentrations go back to their values in equilibrium. So to sum up, we have two configurations, forward and reverse bias. In forward bias, we have a very high current, so the junction, the PN junction or the diode behaves almost as a short circuit, and this current is high because it's a diffusion current, and we have a high concentration of holes in one side, low concentration in the other, and the other way around for electrons. So the gradient is high, the diffusion current is high. And in reverse bias, the PN junction behaves essentially as an open circuit because this current is very low, because it's a drift current that depends on the concentration of holes in the N side and of free electrons in the P side, and these concentrations are very low. And with that, we conclude this important lecture, and in the next time, we're going to begin our quantitative or mathematical analysis of PN junctions out of equilibrium. And I will see you next time.